Hello and welcome to Basic Statistics with Tableau. My name is Tyler, and I'm a software engineer with Tableau software. So today, we're going to learn about a number of basic statistical analyses that can be implemented inside of Tableau. Now, these are things you'll typically encounter in a Stats 101 course and then forecasting. Because, who doesn't want to be able to tell the future? Okay. So first, a little bit about me. That's my email address on there. I love answering questions, so please feel free to send me an email asking questions about anything that you see here today or stats in general. Before I came to Tableau, I wanted to be a teacher. I got about 5 months into my student teaching, and you know what I found out? Teaching was not for me. What was for me, though, was quantitative problem solving. So I went back to UW, I got my master's in applied math, and ended up at Tableau, where I get to engage in quantitative problem solving every day. Now, I still really love the act of teaching, and I really believe that anyone can be a data scientist. So TC is a really great week for me because I get to be a teacher for a week, and then I get to go back to doing linear algebra or numerical analysis. So on our agenda today, we will talk about confidence intervals, hypothesis testing, trend lines, forecasting, and hopefully have some time left at the end for Q&A. If you have questions during, please feel free to stop me and ask them. I might not be able to hear you since this room is enormous, so we have some mics set up right here. Other people may benefit from your question and maybe even my answer, but some of the questions may go beyond the scope of the course, and then I'll ask you to wait until the end. Confidence intervals. So I'm pretty into fitness. And I was timing 1-mile runs for my nephew's elementary school. And so like this guy right here, I was wondering, can I run a mile faster than a second grader? Well, I certainly hope so, but really, I'd actually like to know if I can run a mile faster than like the average second grader in Seattle. But I only have a small sample. So what does my sample tell me about the population? All right, let's take a look at an example. All right, so here's the data set. I have the converted time. That's the total number of seconds for each race. I'll place that on rows. Now, I was curious about how I would stack up against second graders, so I'm going to drag out grade to columns, and we can look at all the grades. I think that's probably fine for now. And then I want this at the level of detail of individual athletes, so I'll place first name on detail. Okay, so there's my sample. What does my sample tell me about the population? From the analytics pane, that's up here, I'm going to drag out average with 95% CI and place that per cell so that I get an average with 95% confidence interval for each grade. Cool. So this gray line in the middle is the average for that sample, and the shaded region is the confidence interval. The definition of a confidence interval is that for 95% of samples, the confidence interval contains the population average. But I only have the one sample. Assuming the sample was randomly chosen, and I think for our purposes it was, there is a 95% chance that this confidence interval for this sample contains the population average. So if I want to know if I can run a mile faster than the average second grader in Seattle, I should be healthily outside of this lower confidence level, which unfortunately I am not. I will stick to weightlifting. But while we're looking at this, I'm noticing something kind of interesting. I'm noticing that the confidence intervals for the first and the sixth grades are larger than for the other grades. Why is that? I'm hearing small sample size? Yeah, that's right. So if I don't have very many data points in my sample, I can't be as sure of where the population average is going to lie. So following that same reasoning, let's say I wanted to change my confidence level to 80 so that I only want to capture the population average 80% of the time. What do we expect to happen to our intervals? They should shrink. Has heard someone say that. And yeah, because we don't need to be as sure, or we don't need to catch the population average as much of the time, so we can cast a smaller net. And we can do that, so I can just right-click on the confidence interval, choose Edit. The confidence level is right here. Let me zoom in from, see things come in. Yep. Zoom in, so I can choose 80. Let me back out. And lo and behold, our interval shrank as we expected. Fun. Any questions on confidence intervals so far? Good, okay, that was it actually. Confidence intervals are something that are often misremembered or just misunderstood. So I put the definition up here on the slide. The definition of a confidence interval is, for 95% of samples, my confidence interval contains the population average. Then, for a particular sample, there is a 95% chance that the confidence interval contains the population average. So we can, from the sample, infer about a population. To review, confidence intervals are good at answering questions like, what does my sample of mile run times tell me about the average second grader in Seattle? Or, is the average second grader in Seattle likely to run a faster mile than me? Turns out the answer is yes. It's all right. Hypothesis testing. So I mentioned I was really into fitness. CrossFit is my sport. Any other CrossFitters here? Oh, seriously, not even one other? Oh, okay. Oh, that's a relief. That was going to be a pretty rough demo. All right, so I watched the 2018 games this summer. The 2018 games is the CrossFit's annual competition, the best in the world. And I thought this year's games was particularly interesting because of the CrossFit total. So the CrossFit total, for those who are not familiar, is a general test of strength. Each athlete will perform 3 max effort lifts, and their score is the sum of the pounds lifted. They're not using metric, unfortunately. Now, the reason why the CrossFit total is interesting, and isn't just because it's really fun to watch people lift heavy things, but because the same event appeared back in 2007. So we can kind of see the evolution of strength in the sport over 11 years. CrossFit has become considerably more popular since 2007, so it's actually a pretty interesting problem. Now, I hypothesized, upon watching the games, of course, that CrossFit Games athletes in 2018 were stronger on average than they were in 2007. So the one CrossFitter in the crowd is going well, yeah, duh. But I'd really like to quantify that for those of you who aren't into CrossFit as much. We will do so with hypothesis testing. Before we go into hypothesis testing, we need a little bit of vocabulary and kind of a roadmap of what we're going to do. A test statistic is a value that is calculated from your data. This value always follows the same distribution regardless of the distribution of your data. So generally, we will find a test statistic that's good at answering the question that we want to answer and use that because the proof for what distribution a test statistic follows is well beyond the scope of our course and generally not recommended. We will not compute a test statistic directly today because doing so is actually kind of difficult in Tableau. But we will be referencing this concept over and over again, so I wanted everyone to have an idea of what it means. Hypothesis testing always follows the same procedure. We will first state the hypothesis and the null hypothesis. So I believe that CrossFit Games athletes in 2018 are stronger on average than they were in 2007. The null hypothesis would then be, anyone? That they're no stronger, that on average, they're about the same. Then we will choose an appropriate test statistic. Does anyone have an idea of what we might use? I heard T out there. A t-test is really good for comparing averages of 2 populations, and that's the one that we're going to use. I didn't expect anyone to know that, I just wanted to see. Okay, then we'll choose a threshold probability. This is going to be some small number, and we're just going to use 0.5% for now. Then we will calculate the p-value. So this is where all the magic happens. This is the probability, under the null hypothesis, of sampling a test statistic at least as extreme as what we observed. And then we can accept or reject the hypothesis. So I mentioned that we would use a t-test, so that's student's t-test. The test statistic follows student's t-distribution. We will use what's called a two-sample location test. There are a number of flavors of t-test, most of which are equivalent in, as far as the two averages or two populations are concerned. But for our purposes, we'll use a two-sample, or what's called a two-sample location test. And this tests the null hypothesis that the means of two populations are equal. So this is really well suited for the problem that we're trying to solve. Oops. Okay. Let's take a look. Okay. So I have the data sets from both 2007 and 2018 all together in one column. My question involves two different populations. So we needed to split them apart with a pretty simple calculated field. This is if year equals 2007, then result, else null. Nulls get ignored by our calculations, and so this will properly give me the 2007 population. The easiest way to perform a t-test in Tableau is to use external services. So we're going to call out to R, have R perform the computation for us, and then bring it back. Now, I understand that not everyone can use external services, or people aren't really interested in writing any code. That's totally fine. This can be done without external services, but doing so is actually kind of beyond the scope of our course. But I have a workbook with the exact same workbook with that calculation in there. So if you're interested, come see me afterwards, shoot me an email, and I think this stuff will get posted after the session is over. But for now, we're going to use the external services, and don't worry, the code won't be too complicated. All right, so to use external services, we start by creating a calculated field. We're going to call this t-test. Actually, really, this is going to be the p-value. In order to call out to external services, all the calculations start the same way. They start with script underscore followed by a data type. Let's zoom in on that really quick. This data type refers to the data we're expecting back from the external service. We want a p-value in this case, so the data type we're going to choose is real. So, script real. Now the fun stuff. The first argument to any script function is the script itself, which we will write last, and that just goes inside of quotes. Next, we have to be able to pass data to the external service. So I'm just going to hand it the 2007 results and the 2018 results. Okay? However, it's still complaining at me. And the reason for that is that all of our external services calculations are table calculations, which means they're computed at the level of detail of the viz, which means that the arguments to them must be aggregated. We are going to end up computing at the lowest level of detail, at the level of individual athletes, so sum is a perfectly fine aggregation for us to use. There. Okay, now for the fun part. We have to write some R code. Typically, I would recommend you develop your R code outside of Tableau and then bring it in once you know that it works, because we don't really do any syntax checking for you, and sometimes the error messages, as you will probably see shortly, aren't super helpful. But luckily for us, this is pretty simple. I'm willing to code it live, which is always a dangerous game, but I'm feeling lucky. So t-test in R, pretty straightforward. T.test, .arg1, .arg2. Typing live is much more difficult. Okay. .arg1 refers to our first argument. That's the 2007 results. .arg2 refers to our second argument, the 2018 results. So we're done, right? Actually, not quite. So in developing the script outside of Tableau, I learned that t.test returns a whole bunch of stuff. We get the test statistic, the p-value, etc. I think like degrees of freedom and a couple of other statistics. I really just care about the p-value right now, so let's get that by doing $p.value. So that's an R notation thing that just says give me back the p-value. All right, ready to rock and roll. Let's place that p-value on text so we can see what it is. and I ran into an unhelpful error message. If you can't see it, don't worry, it really isn't helpful, I promise. So what's the problem here? Well, the script calcs are all table calcs. Table calcs are computed at the level of detail of the viz. What is the level of detail of this viz? It doesn't have one, right? We don't have any dimensions, we don't have anything on there. So we need a dimension to compute along so we know how to aggregate the data that we're passing in. So let's close this. Sorry about that. I'm gonna place athlete on detail, and I need to tell that table calc to compute using the dimension I placed. And just as a general rule of thumb, if you're using table calculations and you run into a problem that you can't quite figure out, check the compute using. That's usually the first place you should look. Make sure you're computing along the dimension that you actually care about. So I want this at the level of detail of individual athletes. So I'll choose athlete, zoom back out, and we can see our p-value. Now, I performed this t-test just for the women's data. Right? I filtered it on athlete sex. Because of the strength disparity between men and women, having both of those things together in the same population could potentially throw off our t-test. So it's better just to try to compare as similar populations as we can. So is this p-value smaller than our threshold probability? Yeah, it's super tiny. This is good. So we can reject the null hypothesis and conclude that CrossFit Games athletes, on average, were different in 2018 than they were in 2007. Does it answer the question that I asked originally? No, not quite, right? I think that they're stronger, but I actually only know now that the averages are different in a statistically significant way. Oh, and sorry, almost forgot. Men's field, exactly the same thing. Also statistically significant. So let's figure out the direction in which those averages were different. So I have a scatter plot of the data here with the years right next to each other so we can kind of compare year to year. From the analytics pane, I'm going to drag out a box plot. And we can see the direction is in the stronger direction for 2018. Especially on the women's side. It's less clear on the men. There was just a much greater spread in 2007, but I would say the central tendency, that kind of the location of the center of my distribution of data, is much higher. And that's really what we're looking for, right? So, CrossFit Games athletes were stronger in 2018 than they were in 2007. You didn't even have to watch the CrossFit Games to know that. Cool. Any questions on hypothesis testing? Yeah. Sure. So we want to see the formula for hypothesis testing. That would be the p-value here. I wonder if I can zoom this in. Oh, I can't. Oh, no, maybe not. That's not making it any better. Okay, yeah, well, let's go plus. I've never done this before on the Mac, so it's always interesting. All right. So this formula should be pretty well useful for almost any purpose. But if you have specific questions, again, please feel free to shoot me an email, and I'll see if I can help you figure it out. All right. Any other questions? I'll leave this up for a second here. Maximum impact. Okay. So this workbook will be posted along with the slides, and another workbook that does the exact same test, but without using external services. All right, moving on. To review, hypothesis testing can answer questions like, are CrossFit Games athletes stronger in 2018 than they were in 2007? Or, are observations of two groups independent of one another? So we didn't look at that example, but that would be a chi-square test, another type of hypothesis test. Or, is my sample drawn from a normally distributed population? That would be a Shapiro-Wilk test. Questions on hypothesis testing? All right. Trend lines. How do age, company profits, and experience relate to CEO compensation? So I wanted to have a picture up here of a CEO, and I thought it'd be really weird if I put Adam Slipsky up on a slide. I don't know him very well. So this is a picture of my cat wearing a necktie. He is the CEO of our house. He is paid in food. Yeah. His name is Malcolm. Okay, before we start to try to relate those age, experience, and compensation, or excuse me, age, experience, and profits to compensation, we need a little bit of vocabulary. Trend lines have a null hypothesis too, but it's a little bit different. The null hypothesis in the context of trend lines is, what if there is no relationship between my two variables? Visually, it looks just like this. It's a flat line through the middle of the data. So keep that in mind. Residuals. Residuals are the difference between the dependent variable value and your fitted values. So in this image here, the residuals are just those black line segments, and we're looking only at the difference in the vertical direction. Tableau's trend lines uses an analysis method called ordinary least squares. Ordinary least squares has a number of assumptions that we need to satisfy before our fitted values and the confidence bands make sense. We'll talk about the confidence bands shortly. I have all these questions in captions in the workbook, so I just wanted to give everyone a quick idea of what they are, and I'll read them off as we explore them. Okay, let's take a look at an example. So, I've boiled those assumptions down to some questions that we want to answer yes to before we believe we can trust our trendline estimates. First question is, do I suspect that there is a relationship between two variables? And what do I suspect that relationship is? So I actually mentioned a lot more than two variables. So what we're going to do is we're going to take age, experience, and profits, and place those on columns as my independent variables, because I'd like to know how compensation changes as age, experience, or profits change. So let's go ahead and place compensation on rows, and I want this at the level of detail of individual companies. Okay. So what we're going to do may seem a little bit backwards, but it's pretty easy, so we're not going to lose any time over it. From the analytics pane, I'm just going to drag out trend line. And because I honestly have no idea what the relationship is between age, experience, profits, and compensation, or compensation, excuse me, I'm just going to choose linear. Okay, so do I suspect that there's a relationship there? Remember what the null hypothesis looked like, right? It's that flat line through the middle of the data. Do these lines look flat? No, so I would suspect that there is a relationship here, just eyeballing it. However, one thing to be really careful of is that because of the axis scaling, it's a little bit different for each one of these fields. So we might get a line that looks sloped when it really isn't that sloped. So we're going to look at the p-value instead. You can see it right there at the bottom. For the relationship between age and compensation, the p-value, that's the probability of getting the same model under the null hypothesis, is about 13%. That's not very good. It is above our arbitrarily chosen threshold probability from the last exercise. But p-values that high generally aren't good. So let's look at experience. See, the p-value is smaller, so that's good, about 2%. And if we come over here to profits, we can see the p-value is really small. Of these three relationships here, the relationship between profits and compensation is the most interesting. Now, one caveat, and this is important. This does not mean that profits is the most interesting of all three. This just means the relationship between profits and compensation is significant, and the relationship between experience and compensation is less significant. This model doesn't actually take into account all three variables. It's three separate models, and we're kind of evaluating their significance independently from one another. In order to use all three variables, that would be a multiple linear regression. That is beyond the scope of our session, but if you're interested in doing that kind of analysis, let me know and I can try to help you out. Okay, so let's dig into profits a little bit more. Now, I definitely suspect that there is a relationship between profits and compensation. And I said, I'm not really sure what that relationship is, so I'm going to say I suspect that it's linear. We're always going to choose the simplest possible model that we have justification for, and we'll see what happens if we make a mistake. But for now, don't worry about it. Next question. Do the residuals have a mean of 0, and do they appear unrelated to the independent variable? Well, it's kind of hard to see what the residuals are because they're not actually points, so we're going to need to calculate them. Does everybody remember what the definition of residuals are? So the definition, I think I saw someone nod back there, at least one. Okay, so I'll tell you again. The definition of residuals is the difference between the dependent variable values and your fitted values. So we need to calculate the fitted values for which we have an equation. So I'm going to create a calculated field on my independent variable because the equation I have is in terms of the independent variable. We're going to call this fitted values. And let's try to zoom in again. Is it control? Oh, yeah. There we go. Okay, what's my equation? Well, it's in the tooltip right here. I'm going to leave my mouse cursor in the calculation window, and I'll just copy this off. 0.933774 times profits, plus, I think it's 993.5. Okay, those are our fitted values. Okay? Then the residuals are just going to be the difference between compensation and the fitted values. Create a calculated field, one more time. We'll call this residuals. Let's make this bigger again. All right, compensation minus fitted values. Question was, do I have to square it? No, not in this case. So I'm just looking at the actual residual values, not the sum squared errors. So sum squared errors is the metric that we use to, or the value we're trying to minimize when we fit the line. But for residual analysis, we just want the raw residuals, not the squared value of them. If that makes sense. Good question. I like it. Okay, so residuals. Let's do some residual analysis. The calculation that I just created is dependent upon this trend line. This trend line is computed at the level of detail of this viz, which means the calculation I made based on this equation, that one up at the top, only makes sense at the level of detail of this viz. So when I go to do my residual analysis, I'm going to place company on detail because that was the level of detail that I had. Then we'll place residuals on rows, and there's something in here about the independent variable, so I'll place that on columns. All right, that's what my residuals look like. Do they have a mean of 0? All right, from the analytics pane, I'm going to drag out the average line and just throw that on residuals. And we can say that, yep, they sure do. Do my residuals appear unrelated to the independent variable? They do appear unrelated. There is a little bit of clumping here, right? But they're not rising and falling together with the independent variable. And that's really what we're looking for, right? We're looking to see some kind of relationship there. And indeed, these are an example of residuals for a model that has been correctly specified. Answering questions 1 and 2 are enough to guarantee that your trendline estimates make sense. But we want to know, perhaps, or how sure we are about where the true model lies, right? There's a true model somewhere out there. We tried to estimate it here using trend lines. But what if we want kind of a visual indication of that uncertainty? In order to do that, we have to answer 2 more questions. And it looks like they're related to the residuals in some way and the independent variable. So I'm just going to make exactly the same viz that I made before. We'll place company on detail, residuals on rows, and profits on columns. Are the residuals unlikely to be correlated with one another? So this really comes from a knowledge of the data itself. You can think of residuals as a measurement error. Is the error in any particular CEO's compensation likely to be related to the error in another CEO's compensation? What I know about this data set, I don't think so. These companies are from all different fields and markets, so I would say that I believe the residuals are unlikely to be correlated with one another. So that's good, yes. And then does the spread of the residuals look roughly the same with changes in the independent variable? Well, the clumping here is actually not really a concern because we're looking at kind of the spread, the space that the points span. And it looks about the same actually, except maybe we have this one point all by itself out here. But I would say for the purposes of basic stats, this is good enough. So we can trust our confidence bands. There's our line. I'm just going to right-click on the line. Oops. Edit trend lines. And then check the box that says show confidence bands. Confidence bands are very similar in concept to confidence intervals, in that they give you a range in which the true model is likely to lie. So just like with our confidence intervals, we can see that when we have a lot more data, we're a lot more sure about where the true model lies than in the places that we don't have as much data. Okay, so that was easy. I got it right in the first try. What if my data, or what if the linear model was the wrong model, right? We just kind of brazenly guessed linear and ran with it. How many people have done the online training for trend lines? Okay, don't worry about it. There's a data set on here called the windmill data set for which the model is nonlinear. But let's suppose I haven't done the training and I just guessed linear. So we're going to see what happens and how we can recover from that error. So I want to know how power output for a windmill relates to wind speed. So power output goes on rows as my dependent variable, wind speed on columns as my independent variable, because power output is going to depend on wind speed, certainly not the other way around. And I want this at the level of detail of individual windmills. Okay, do I suspect that there's a relationship there? It certainly looks like it to me, yeah. So from the analytics pane, I'll drag out trend line, and we're just going to brazenly choose linear because, you know, it's the simplest model, and let's pretend I know nothing about windmills. Okay, does that look like it's a pretty good fit? Yeah, it is a pretty good fit, actually. But when we go to do the residual analysis, this is what they look like. Do my residuals have a mean of 0? Drag out that average line, place it on residuals, and we can see that, yep, they sure do. But do my residuals appear unrelated to the independent variable? I'm seeing some shaking heads. So these are an example of residuals for a model that has been misspecified. We chose the wrong type of model for the data. And so you can see that they all kind of start together, they come down, they come up, and come down again. So these do appear related to the independent variable, which means I need to choose a different model. Same data as before? Well, if linear didn't work, I can just try logarithmic. There are only 5 models here, so hopefully I'll run into the right one eventually. Is that a good fit for the data? Definitely not. So we don't even need to do the residual analysis. I know they're going to look terrible. Let's just move on. How about exponential? It's going to have the same problem, right? Well, only 2 to go. Polynomial? Oof. Ooh, I got goosebumps. Yeah, that looks good. Cool. So that fits the data really well. I didn't look at the p-value for the last one because I was pretty sure of the slope, but we can look at the p-value for this if you'd like. We can see that it is super small, so this relationship is significant. How about the residuals? That's what they look like. Mean of 0. Oops, place on polynomial residuals. Yep, they have a mean of 0. Do these appear unrelated to the independent variable? Yes, they do. They're just kind of scattered around 0. Now, there's a little bit of clumping up here, but again, clumping isn't really that much of a concern. Really, we're looking to see if they rise and fall together, rise or fall together. So, our model was correctly specified. Yeah. One other thing, though. Now, when I drag out the polynomial model using the analytics pane, it chooses a degree 3 polynomial by default. We got a little bit lucky here, because if you know the physics of windmills, which I do because I read Wikipedia shortly before doing this, you'll know that the relationship between wind speed and power output is a cubic relationship. So we actually got the correct relationship right away. We can do the same analysis by choosing a degree 2 polynomial, and we'll see similarly crappy residuals. But what happens if I go past degree 3, right? If sum is good, more is better, right? So let's right-click on the trend line. I'll edit it. And here is the polynomial degree stepper. And I can just crank it all the way up to 8 as far as it'll go, because A3 polynomials are great. Does this fit the data really well? Yeah, this is a great fit. And I can guarantee you the residuals look really good too. But is this a good model for our data? So let's take a look at what this model is telling us. Maybe we can zoom out a little bit. This model is telling me that at about 17 meters per second, for some reason, power output just falls off. And then shortly after 19 meters per second, wind speed, power output goes blasting off to infinity. Is that a reasonable model? No. So the data don't really support that kind of behavior. And indeed, this is an example of a model that has been overfit. We chose a model that was too complicated than what was supported by the data. So this is why I always say choose linear first, because it's the simplest model, and generally stick to the simplest model that you have justification for. In the windmill case, I have justification for a cubic model, but nothing any more complicated than that. Okay. Any questions on trend lines? Yeah, one in the back. Oh, the question is about R squared. So R squared is pretty easy to manipulate, and so that's why I didn't really talk about it too much. So you'll notice on this little tooltip here, we have R squared. For this model, R squared is like ridiculously good, right? It doesn't necessarily mean that's a good model, but what the R squared means is how much of the variance we've explained. So this model explains 98% of the variance that we have here. If we go back and look at, say, like the linear model for, I think this one, yep, this sheet here, we can see the R squared explains, or this model explains 95% of the variance. So as you're changing your models, you generally want to explain more and more variance. However, that can lead you into overfitting. So I figured for the purposes of basic stats, we're just going to focus on fitting the simplest model that we can. But the R squared is a good way of saying this model has explained this much of the variation in the data that I see. Does that answer your question? Yeah, cool. Sorry, they're really bright lights. I can like barely see you back there. All right. To review, trend lines are good at answering questions like, what is the relationship between profit and CEO compensation? When wind speed changes, how does windmill power output change? Or does compensation change in a meaningful way when age changes? Last but not least, forecasting. So the forecasting generally will not appear in a Stats 101 course, but it's pretty easy to do in Tableau, and I hear it's pretty useful. No, I'm just kidding, of course it's useful. So now, when I was making this demo a couple years ago, I had some boring example about a souvenir shop in Australia. But then I found this post on Reddit, and I noticed there's kind of a pattern in the number of times that All I Want for Christmas Is You gets played at the end of every year. So the data is actually old. It's from 2016. Since then, YouTube has changed how they create their charts, and so in order for me to get the real data from them, I need an API key, which I don't have. So we're going to do this on old data, but the concept is still the same. So how many times will All I Want for Christmas Is You be played in December of 2016? Let's find out. So I have the data right here. I'm going to place page views on rows, place date on columns, and I want this at the month level because I'm curious about December of 2016. In order to forecast, I just go to the analytics pane, choose forecast, drag it out, and boom. All I Want for Christmas Is You will be played, well, or was played 49 million times in December of 2016. Great. Did you guys notice we didn't need to choose a model type? Yeah, this is pretty great. So Tableau's forecasting uses a method called exponential smoothing. Exponential smoothing weights observations in the recent past more than observations in the distant past. And you can see that's actually reflected here, right? The number of views is certainly growing every year, although only at a certain time of year for some reason. And we compute 8 different exponential smoothing models, and we choose the best one based on AIC. AIC is a relative quality metric, which tells you if it's the best model of the ones that you've computed. But given that it's a relative quality metric, does it tell me how reliable my estimate is? No, not really. So we need to know, or it'd be nice to know how reliable this is. So if I'm going to go and tell someone that I think All I Want for Christmas Is You will be played 49 million times, that I have some reason to believe that. So we need to talk a little bit about model quality. For the purposes of basic stats, we will consider only one model quality metric, and that is the MAIS, the mean absolute scaled error. MAIS compares the error of your model with the error of the naive forecast. MAIS is typically between 0, which is good, and 1, which is bad. MAIS can be higher than 1, and that's just really bad. The naive forecast. The naive forecast is just the forecast that copies the values from the last observed value. For seasonal values, it just copies the values from the last observed season. So generally not a great forecast. Okay, let's take a look at the MAIS for our forecast. All right, so same forecast from before. I'm going to right-click on the viz and choose right-click on the viz and choose Describe Forecast. Now you can see we have a little KPI quality indicator here, but this is basic stats. We can go a little bit deeper than that. We'll click on the Models tab, and we'll see the MAIS right here in the middle at 0.41. So this forecast has 41% as much error as the naive forecast. So much better than just copying the values forward, but it's only okay. Does anybody happen to know how many times All I Want for Christmas Is You was played in December of 2016? No, I didn't expect you guys to know. I'm just curious. Okay, cool. How many people have used forecasting at least once? Show of hands? Oh, good, quite a few of you. How many people got a forecast that they didn't expect? Okay. Oh, actually, that's not as many as I thought it would be. So I certainly have. I have definitely gotten forecasts that I didn't expect. What can you do about that? Well, part of the reason that we're using forecasting is we really don't know what to expect. And so the forecast you don't expect may actually be the best forecast for the data. However, there are times where the forecast is not a great forecast and it was what you didn't expect. So we're going to look at a couple of different scenarios and what you can do about them. The structural break scenario. So we're going to look at this in the context of my t-shirt inventory. So I've been keeping inventory of my t-shirts since college. Don't ask me why. But I have all the data right here at the quarter level. So I'll place number of t-shirts on rows, and then date on columns at the quarter level. Okay, so where will my t-shirt inventory be after 2018? Well, from the analytics pane, just as before, I'll drag out forecast. So didn't quite expect that. That just tells me that I will have the same number of t-shirts indefinitely. Seems a little strange because the number is doing other things. But is this a quality forecast? Well, we'll right-click on the viz, describe forecast, and we can, oops, zoomed in too soon. We can see the MAIS is a whopping 1.4. So this has 140% as much error as the naive forecast. Not a quality forecast. However, I think that we can do better. The reason I think that is because I'm noticing kind of a structural break here in the data. It looks like there are at least 3 different data generating processes. So story time. These are the data from when I was in college. Didn't have a whole lot in the way of t-shirts. But then suddenly I got a job at Tableau. So now I have lots and lots and lots of t-shirts. And that held on for a little while up until we went to quarterly releases, at which point they decided that giving us a t-shirt for every release is probably not the most sustainable solution long term. So we started getting patches instead. So then after that, my t-shirt collection kind of declined steadily over time with a little bump every time we have a conference. So when I have a structural break in my data, I can filter out the points preceding the break to see if that improves the quality of my forecast. Remember I said that our forecasts use exponential smoothing, which weight observations in the recent past more than in the distant past? So we really want to try to focus it on the recent past as much as we can. It's still taking into account these points, and it could be throwing off my forecast. So when forecasting is active, because of how it works on the back end, we can't actually filter and exclude the points directly, so we'll need to filter on the date. So I'll right-click on my date, choose Show Filter, and then let's just filter out the data from the time when I was in college. Probably about there. All right, is that looking better? Yeah, it certainly looks better to me, but we need to know if this is a quality forecast. Describe forecast. And the Models tab. See, the maze is down to 0.56. That's great. Much better than before. 56% as much error as the naive forecast. But I think we can do better still. Remember when I said Tableau stopped giving us t-shirts for every release? That's a new that was a new data generating process. So let's go ahead and filter out this other structural break here. And we can see that looks even better. Let's just see if it's a quality forecast. And we can see that, yep, the maze is down to 0.47. 47% as much error as the naive forecast. So that's good. Any questions on structural breaks? I don't see any. OK. One more. We're going to talk about my magic card collection, or the value of my magic card collection. So I was moving recently. My wife found all my magic cards. And she was like, oh, Tyler, can we just get rid of these things? I said, no, Jen. Their value is going up over time. Look at this chart. So of course, I went to the analytics pane, drug out a forecast, and oof, yeah, that's not so good for me. However, I don't know if this is a quality forecast. Let's find out. Let's try forecast. This has 99% as much error as the naive forecast. But I think that we can do better. The reason I think that is because notice how spiky my data is. And now, I don't really care about the short-term value of my magic card collection. I care about the long-term value. There may be too much short-scale variation at the current date level, and that may be throwing off our forecast. So what I can do is, I have this data at the week level right now. I can aggregate up from week to month to see if it'll smooth out some of that short-scale variation and give me a better forecast. So going up to month, well, has the same problem, but maybe this is the best forecast for the data. Well, let's go ahead and describe forecast. We can see that the maze is 0.87, 87% as much error as the naive forecast. So it's better, but still pretty poor quality. Now, I said earlier, if some is good, more is better. So we can try going from month to quarter. And to see, really it's because I see a lot of short scale variation in the data. So going from month to quarter, this is better. Is this a quality forecast, though? It's OK. 60% as much error as the naive forecast, but much better from where we started. So of course, I showed this to my wife, and she's like, yeah, totally keep the cards. No, I got rid of my collection. It's gone. All right. Any questions on short scale variation? Nope? All right. Oh, yeah. That's a good question. So the question was, could I get the same result by, say, using like a moving average to kind of smooth things out? With Tableau itself, no, because you can't forecast on a table calc. Because of the way it was implemented, we aren't able to do it that way. But forecasting itself really is just a very complex moving average. So it is doing some smoothing there along the way. It sees that variation and tries to account for it, and that's really the problem. So I definitely would recommend aggregating up rather than trying to forecast some kind of moving average. Because it'd be kind of like creating a moving average and then creating a very complex moving average on top of that, which isn't necessarily what you want. Great. Oh, sorry, next slide. All right, we already talked about those things. And to review, forecasting is good at answering questions like, how many visitors can I expect in the future, to my page, excuse me, can I expect in the future given data on past visits? Or, based on past data, what will my inventory be in the future? Or, how is the value of my collection likely to change in the future? Any more questions on forecasting? Anything as a whole? No? Great. All right, well, thank you guys so much for coming. Please.